Okay. All right. So what we're going to talk about now is phase noise, and we're using sort of an academic phase noise 101 to mean this is an introduction to the topic of phase noise. We'll talk about some basic aspects of it and why it's important, and especially for aerospace and defense, but also commercial communications, digital communications, and then talk a little bit about how the measurements are actually made. So this is an introduction, and there will be a little bit of trigonometry, but I assure you it's very simple, and there's no test at the end. So just enjoy it, and hopefully you'll walk away with a better understanding of what phase noise is and why we are concerned with it in the performance of RF microwave and millimeter wave equipment used in our industry. So let me start first by talking about what is phase noise. So if you look at any kind of a signal, a carrier of information, it has a frequency, right? Whatever it might be. It could be 100 megahertz if you're tuning to an AFM radio. In cellular, it might be a gigahertz or 2 gigahertz. And we generally make the assumption that that frequency is constant. It may have some modulation on it to carry the information we care about. But in the real world, that frequency is not exactly constant. And there are really two types of instabilities. There is long-term frequency change. Normally we call that drift in frequency. It's a deviation around the nominal frequency, and it could take place over minutes, hours, or years. Normally that's a function of something that is aging, maybe the reference oscillator or some change in the physical parameters of the system. There's also short-term frequency instability, and that is something that we usually look at on an instantaneous basis. So typically non-stochastic processes, noise, thermal effects cause very short-term frequency instability of my carrier signal, and that is what we will focus on today, and that is the type of frequency instability that is associated with phase noise. So long-term and short-term, we will talk primarily about short-term frequency instability today. So here we go with a little bit of mathematics. So if you think about a typical carrier, it's a sinusoid, right? Hopefully everyone understands the basic principles of sinusoidal signals. If we look at them in the time domain on an oscilloscope, they look like the signal on the left. So it's changing amplitude and going from a positive peak to a negative peak as a function of time at some type of a rate. That's in the time domain. If we look at that same signal in the frequency domain, we represent that as a single vector with a certain amplitude at the frequency of interest, the nominal frequency, or f sub 0. And the formula for the amplitude and voltage of that signal is expressed as some nominal amplitude, a sub 0, times the sine of 2 pi of the frequency as a function of time. So that's the ideal world. But in the real world, we know things are a little bit different. We have noise, and there are actually two kinds of short-term noise that can be associated with that signal. There is amplitude noise, which shows up as an amplitude term, and you see that on the time domain graph on an oscilloscope, with some changes in amplitude fluctuating randomly about a nominal value. And then there's also maybe a change in the sinusoid itself on the x-axis. So that's a change in phase or a change in frequency. Actually, the frequency is the first derivative, the change in frequency of the change in phase. And so that's represented by the second formula. I won't read it here, but you can see there is an error term associated with amplitude. That's E sub t, adding in to the nominal amplitude, and there is a phase term associated with the Greek letter phi as a function of time. So there's a phase component that's adding to the normal 2 pi times the carrier frequency of interest. And in the frequency domain, what we see now is a spreading of that carrier with some sidebands and also some noise. Looks like noise in the frequency domain, the lower right-hand corner behind me. So what the phase noise is actually a way to talk about what is the amplitude of that sideband the SSB, relative to the carrier power, P sub 0. And we'll see in a few slides that in the case of phase noise or noisy changes, random changes in the phase of the signal, instead of seeing sidebands as are shown here behind me, we actually have noise skirts on both the upper and lower side. The nature of these random, short-term, instantaneous changes in phase are such that they apply to both the upper and lower side of my carrier of interest. Now, when we talk about making phase noise measurements, we will just focus on measuring the upper sideband because of the symmetry property. If we just measure the upper sideband, we can determine the overall phase noise of a signal of interest. Okay? So we will be focused on the upper sideband when we get to making measurements. But you'll see in a moment, it's really about measuring that level of the sideband at a certain offset relative to the fundamental carrier frequency. So the number or the dimension that is associated with phase noise is a measurement of spectral density in a certain nominal bandwidth. Normally it's 1 Hertz bandwidth relative to the carrier power. And so it's represented as dBc. dB relative to the carrier per Hertz. And it's always specified at an offset frequency. So normally you might see a spec of a phase noise of minus 130 dBc per Hertz at a 10 kilohertz offset, as an example. And that's always relative to f sub 0, the carrier frequency that I'm measuring at. And it's a power spectral density because we are measuring a stochastic signal. It's not deterministic, it's noise-like. So you might have a certain amount of amplitude in one instant and then it changes. And so we use that as a way to specify spectral density within that bandwidth, normalized to 1 Hertz. The script L of F is actually the phase noise. So script L of F means the phase noise at that frequency is in dBc per Hertz. Now, to understand a little bit more about what is causing phase noise to occur, it's useful to go back to phasor diagrams. If you remember your vector math in high school or early college, we used phasors to describe direction, velocity. You use phasors in all kinds of aspects of physics. Here we are using phasors to describe the amplitude and phase of a carrier signal, the main signal of interest, then is modulated in amplitude or in phase because of other signals that are on the tip of that arrow. So for example, in SSB, single sideband modulation, we actually have just one additional vector rotating clockwise around this main amplitude and carrier frequency. In the case of AM modulation, there are two phasors that are orthogonal to each other, rotating in opposite directions and cause just an amplitude variation in the fundamental carrier amplitude. And in the case of phase noise or phase modulation, we actually also have two signals rotating in opposite directions, the upper sideband, lower sideband, that actually cause not an amplitude variation, but a PM variation. And actually there is an AM component as well, but it's the PM, the phase modulation, that we are interested in characterizing as phase noise. So another bit of math here that I want to introduce is that I mentioned sidebands earlier in a case of a AM modulated or FM modulated signal. And so in the case of sidebands, we can use Bessel functions to calculate the amplitude of those sidebands. And so I won't go through all of this in detail, but the first and second and third order sidebands are really determined by the amplitude of the Bessel functions relative to the carrier, which is J sub 0. And in this example, this is just an example. If we had a modulated carrier with a modulation index of 3, this is what the Bessel functions look like. And if you go to an M of 3, modulation index of 3, and measure the amplitudes of those first few Bessel functions, J sub 1 through maybe J sub 10, you can start to see what the sideband amplitudes are. And for example, here, on this chart, the carrier is at the center frequency. You see that the carrier is partially suppressed, right? Because at the modulation index of 3, my carrier has actually come down to an amplitude of an absolute value of 0.25. This is in millivolts, so you see about 250 millivolts here. The first sideband Bessel function, the amplitude at m of 3 is about 0.32. So here, a little over 300 millivolts. The second order Bessel function is here, and its amplitude is actually slightly higher at almost 500 millivolts. So that's that peak here. So you can see that by going from the Bessel functions to the display of our analyzer, we can start to see, for a given modulation index, what is the amplitude of that sideband. Now, in the case of phase noise, remember it's a random effect, right? It's generated thermal effects on the physical characteristics of transistors or other components in my oscillator or my device under test. So we actually have an infinite number of Bessel functions, and as a result, what we start to see is our noise skirts that I showed on the prior slide here. So these here are just the amplitudes of basically an infinite number of sidebands that are rolling off at a certain rate. Okay. Now, something that is important and is a simplification of the math when we get into phase noise is that if we are looking at just small changes in the phase relative to the carrier of less than about 0.2 radians, you can see something very interesting happens. So for small changes in phase, very close to the main frequency of interest, the slope of the first Bessel function, the first order sideband, is almost linear. It doesn't turn into a sinusoidal shape until maybe we get to 0.5 or 0.8 radians. So what we can determine from this is that we can actually simplify the prediction of the total amplitude of a sideband if we make the assumption that we're talking about narrowband phase modulation, which is the case for phase noise measurements. So now we can predict that the amplitude of the sideband voltage will correspond to the slope of this linear line that approximates the shape of the first Bessel function up to about 0.2 radians of deviation. And it's literally just the slope, which is 1/2. So for example, at 0.2 radians, we will have a voltage that is about 1/4, 0.25 volts, okay, as an example. Now, if we want to make the measurement of the relative amplitude, we just do the simple math here, and we can make the approximation to a great degree of accuracy that the ratio of the sideband amplitude to the amplitude of the carrier, V sub c, is 1/2 times the peak phase deviation in radians. So that's the voltage ratio. And as I mentioned before, phase noise is actually a power measurement. So we want to convert that to a power ratio. And from Ohm's law, you know that power is V squared over R. In this case, we are doing a ratio, so the R term falls out. We end up just having to square the voltage of the sideband relative to the voltage or amplitude of the carrier. And so do that, and it means that the power ratio now of the sideband to my carrier is 1/4 of the square of the peak phase deviation expressed in radians. If we look at the same curves, these amplitudes, in the logarithmic domain or logarithmic scale, you can see why this approximation works up until about 0.2 of a radian. So this is a log plot of the carrier amplitude relative to unity, so 0 dB. The first sideband in this particular case starts at a very low relative amplitude and is still about 20 dB down, or 1/100th the voltage of the actual carrier, up to about 0.2 of a radian. As you get to wider phase deviations, the error term becomes much larger, but up until about 0.2 radians, or plus or minus 14.5 degrees, this approximation holds very nicely. We don't have to worry about calculating all these other sidebands. So now if I come back to a spectrum analyzer display, we can see how this might look. If we just focus on the first sideband, we measure the relative amplitude of these two And that will give us a dBc ratio on the screen. If you look, it's probably hard for you to see, but this marker delta function is actually relative, minus 45, minus 46 dB amplitude relative to the carrier. So this is just a simple modulated signal. We're not yet doing a noise example. We'll get to that in a few minutes. So another important consideration is that this is not a deterministic signal. Phase noise is noise-like, right? Random amplitudes with time. So we actually are more concerned with the RMS, or the root mean square average phase deviation, and we will use that to calculate the actual phase noise. So if you remember the relationship for a Gaussian or a random signal, the conversion from peak to RMS amplitude is just multiplying the peak or dividing the peak by the square root of 2. So in this case, this formula applies. The RMS will be the inverse of that. So the RMS voltage is going to be 0.707 times the peak, or the peak phase deviation. Excuse me, the RMS phase deviation will be 0.707 times the peak phase deviation. And again, we want to get to power. So the formula at the bottom, if you can see that here, it's a little bit difficult on this. It's a little bit clearer over there. It's just the square root of the power in the sideband over the power of the carrier times the square root of 2. And that translates back to the RMS phase deviation in radians. So now let's take this case of single sideband or sideband modulation for an FM signal and apply that to a noise situation. So remember I mentioned for a noise-like signal you have an infinite number of sidebands. So we're measuring spectral density, energy normalized to 1 hertz. And so in this case, when we measure the actual spectral density of the phase noise power, we are going to end up measuring all of those sidebands, an infinite number of sidebands that are roughly shaped like that, the skirts of the energy relative to my main carrier. And so the actual final formula for that is at the bottom. The phase noise is just all of the spectral density added up divided by 2, because we only care about the upper sideband. It's symmetric. Okay? So think of phase noise as just an infinite number of sidebands, infinite number of Bessel functions, and we can get back to this formula. If we now integrate all of those amplitudes on the upper sideband, lower sideband, we can describe the single sideband or the double sideband integrated phase noise. And that is another measurement that we can make very easily with our measurement equipment. As another way of describing the noise-like considerations on my carrier frequency. So it's basically just measuring all of the power under those side skirts. And there you have the other formula to get from that measured power back to the RMS phase deviation. Now, some of you might also have heard the term of jitter before, especially if you're working with digital signals. So jitter is just the time domain representation of phase noise. And so in terms of jitter, we actually just take the phase noise, the RMS phase noise, and divide that by 2 pi radians, okay, because what we want to see is what is the percentage of the complete circle times the period to get the jitter. And so jitter is useful if you are looking at a clock and the impact of that on your digital bit stream of 1s and 0s. And you'll see a little later that jitter is the language we use in the digital world if we are designing physical media for transporting digital data. Those engineers concerns themselves with digital jitter. Radar engineers focus more on phase noise, but they are complementary, and one can be derived from the other very easily. Right. So now coming back to a spectrum analyzer, which is one of the tools we can use to measure phase noise. You probably already got a hint of this from the earlier pictures I showed. We are just going to make power measurements of the noise at a specific offset relative to the carrier frequency or the center frequency. So my main signal is at the center of the screen, but the phase noise skirts, the random phase effects will be to the right and to the left, and we can measure that very easily on a spectrum analyzer using markers. In this case, it's a delta power marker. We measure the power at this offset, which in this case I believe is at a 1 kilohertz offset. And we then just do a very simple calculation with the computer that we have in our instrument, measure that level relative to the carrier, which here we've set at 0 dBm. And you can see that the readout is expressed in dB per hertz here. And then if we do it relative to the carrier at 0 dBm, it will be minus 121.3 dBc per hertz. So that's an example of making a phase noise measurement manually. It's the RMS phase noise translated into the power ratio of dBc per hertz. And again, these measurements are typically made at a known offset. And if we want to get the integrated phase noise that I described before, we would be measuring all of the power all along here relative to the carrier. But typically it's made at a specific offset, 1 kilohertz, 10 kilohertz, or could be 100 megahertz, depending on what the requirements are that you have for your application. So that's a little bit of the mathematics and how we derive phase noise. Let me talk a little bit about the types of noise effects that cause phase noise to exist. So the first one is thermal noise, background thermal noise. This is background radiation, black body radiation, everything in the cosmos. And that is constant as a function of frequency. And it's a function really of the temperature that you are at. In this case, the formula is based on a couple of key parameters. It's temperature in absolute degrees Kelvin and Boltzmann's constant. And if you do that calculation for room temperature, most lab environments, you end up measuring a thermal noise power of minus 174 dBm per hertz. Okay, it's normalized per hertz just like phase noise was. And that gives you sort of your basic noise floor below which you cannot really make any kind of power measurement. All right, so we talk about KTB as being typically the best sensitivity that you could ever reach in a spectrum analyzer. Of course, if you had it super cooled and were making measurements at lower than 290, you would be able to measure even lower absolute power levels. But for most lab environments, most of our applications, minus 174 is the practical limit. Now, if we talk about phase noise, there's an interesting fact here is that in the phase noise world, we actually see that there are two types of modulations that are affecting the amplitude of my carrier of interest. There is some phase modulation and there is some amplitude modulation. So you actually have, back to our phasor diagram, you have this situation of two sources of noise, an AM noise component and a phase noise component. We don't care about the AM noise. We want to measure phase noise, just these instantaneous deviations in phase of my carrier frequency. So because energy and the equipartition principle of energy, if you remember your high school physics, those 2 degrees of freedom have similar amplitudes, and we end up only measuring the phase component. So what that means is we actually can measure 3 dB lower in the phase world than KTB because we're ignoring AM. So actually the quote noise floor in most lab environments for phase noise is 3 dB lower or minus 177 dBm per hertz. It's because we're just measuring the phase term and we're ignoring the AM term. And the table on the right tells you that we actually could have cases where if we have more than 0 dBm of carrier power and an infinite dynamic range on our analyzer, we can make measurements of phase noise relative to the carrier of greater than minus 174, in this case minus 177. And we have already done tests in our lab where if we have a 1 watt transmitter that's exceptionally clean at far offsets, we might have a phase noise of better than minus 180 dBc at far offsets as an example. So extremely high dynamic range is possible if you have a good receiver, a good system. So that's a quick overview of that. thermal noise. But there are other causes of noise in physics, especially when you have transistors. There is one common noise property called the 1/f noise. It's a noise that decreases at the rate of 10 dB per decade as a function of frequency, and it's directly correlated with the overall power level. It corresponds on a dB for dB basis, but it's a very predictable -1/f, or a f to the -1 power curve, and on a Bode plot or log plot, it looks like a straight line. It just comes straight from 0 at the carrier frequency till it hits the thermal noise floor. That's called the corner frequency between 1/f noise and broadband thermal noise. So you'll see a little later on that most of our displays of phase noise have some 1/f component associated with them. There are different types of transistors, so there are additional types of noise depending whether it's a BJT or a FET or other types of topologies. So in addition to the -1/f to the -1 noise, there is white FM noise, which has a 20 dB per decade roll-off, flicker FM, and something called random walk. And all of these are based on physics. Different types of systems will have slightly different amounts of each that contribute. It's a function of the physical properties of the semiconductors and other circuits that you have in your device or in your system. The graph on the right shows what those 3 or 4 different types of noise may actually look like on the measurement screen, so you can see the different slopes on the log-log plot of those noise effects. So you can see we have flicker noise and white FM noise, and looks like a little bit of random walk going on as well. So that's a typical phase noise graph on the right. And again, we're showing dBc here, or dB of the noise sideband skirts relative to the carrier at 0 dB. Okay, so that's a little bit on some of the fundamental theory and sources of phase noise. Let's talk now about the applications. Why is this really important to us? So in a typical radar, this is a simplified block diagram of a Doppler radar receiver. We have a transmitter and a receiver. There's a local oscillator that is used to provide reference and also act as a means of down converting the reflected signals that we are trying to capture off of a target on the receiver side. And one of the facts of radar is, unfortunately, there is a lot of signal path propagation loss between the transmitted energy of the pulse and the reflected energy that's coming back. And in the case of a moving target, as Richard explained in his presentation on radar fundamentals, there is a little bit of a Doppler shift of that reflected signal. And so the problem is that if we have a very high phase noise local oscillator, or maybe we have a lot of phase noise in the transmitter, the reflected energy, because it has traversed a fair distance, is highly attenuated. And it could be that that Doppler reflected signal is actually buried underneath those noise skirts. Okay? So what's happening is the phase noise, the short-term narrowband phase modulation on that is causing a spread in the energy, and I cannot actually discern or discriminate and determine the reflected signal coming back from my target. It's also a problem for stationary objects, because remember, this could be a moving platform. There may be less Doppler shift, but the closer the reflected signal is to the carrier, even removing the carrier doesn't help, because of the associated phase noise is still there and will prevent me from being able to actually extract out that reflected signal, which I need for my radar system to work. So for this reason, in the radar world and EW world, I'm characterizing the phase noise of oscillators, references, the exciters, and of course any other devices that are in the RF signal path is very important. In the communications world, I won't go deeply into digital wireless comms here, but when we modulate the digital bits onto a carrier, it's done in such a way that we represent ones and zeros with different points on the phasor diagram. It's a complex modulation scheme. And we use that, we call that typically an IQ or constellation display. And so if we have a perfect oscillator that's doing the, providing the source for the quadrature mixing of my RF to modulate information on the carrier, you get very nicely described dots in their appropriate points on the constellation diagram. However, as you can imagine, if there is some slight changes in phase or frequency of that LO, we get a smearing effect, and now those digital bits, as they're represented in the IQ constellation diagram, get spread, get shifted or smeared. And for a low order modulation like QAM, may not necessarily be a big issue, but as you get to higher order modulation schemes that are typical in most modern communication systems, this is an example of a 64 QAM modulation, you start to see that as you get far away from the origin, that smearing effect can get pretty wide, and if it gets too wide, you'll get decision errors in the receiver, and the bits will be incorrectly received by the receiver. So that's the case in the digital world, digital communication specifically, where jitter or phase noise of the LO used to downconvert a received signal can become a big problem. This picture just shows you what happens when you use different signal generators from the KEYSIGHT catalog as the local oscillator for a high frequency down converter. So we have a digitally modulated signal, in this case a QPSK signal. We generate that and upconvert it using the instrument on the top, the PSG, and then our local oscillator that's used to down convert it into a scope or some sort of a baseband receiver is interchanged. And you can see that the quality, which we describe as EVM in the digital comms world, varies depending on which generator I used as the local oscillator for the up converter. Sorry. And so you can see the EVM is actually the best with the PSG, which turns out is our top of the line microwave signal generator, has excellent phase noise. Some of the more economy priced generators have slightly less or poor phase noise, higher phase noise, and the EVM is slightly higher, about 2.1%. So the choice of local oscillator and its phase noise performance is an important criteria when building a digital communication system. This just gives you a little bit of a close-up view of phase noise for those different generators, and it's kind of hard to see with the lights turned on. But for example, the PSG, which is the yellow line, has a very good phase noise close in, and also the far offset phase noise at wider offsets is very low. The EXG and MXG, on the other hand, have slightly higher far off phase noise, and they have different levels of close-in phase noise in this pedestal region here. The MXG is the light blue line. The EXG, which is a more economically priced signal generator, is the purple line. So most data sheets for generators, especially instruments, will have these types of graphs associated with them so you can get a precise idea of the typical phase noise at different offsets. And again, just a reminder, it's always relative to the carrier amplitude at 0 dB and then measured on a log plot. Okay, so that's an example measurement. Okay, so now getting into how do we actually build receivers to be able to measure phase noise. Okay, so there are two major approaches, and the most common one and the one that I've used to show you these graphs is using a spectrum analyzer. It's called the direct spectrum method, and we literally are just feeding the signal of interest right into a spectrum analyzer. This is a superheterodyne system. We're down converting the energy of that signal to a baseband, digitizing it, and displaying that. The biggest advantage there is it's simple. It's easy. You just feed in the signal under test from your oscillator or VCO or whatever it is you're trying to measure right into the analyzer, and it gives you a display in dBc per hertz, right? Phase noise that we're after. The challenge or the problem with that approach is, while it's easy, is it's not very sensitive. And the reason for that is if you look at all those down conversion stages all those electronics, they are adding noise to the signal of interest. So your sensitivity or your ability to resolve very low phase noise is affected. So for high performance measurements, and typically that's in our world of radar, stalos and exciters, we use a different approach. It's called the carrier removal technique. And in this case, we use something called a phase detector, which is actually a double balanced mixer, but we don't have all of those down conversion stages. We just go right into a mixer, and then we end up using a reference signal generator as the local oscillator for that system. So it's just a one stage, and we end up focusing on measuring the delta between the input phase noise of the signal under test and some kind of a reference. So a phase detector basically is just that. It is a delta function measuring device. It measures the instantaneous difference in the phase of an input signal, the signal under test or signal number 1, relative to a reference, and we just have to control the frequency of the reference to exactly match the frequency of my signal of interest. And you'll see in a moment we also want to control its phase pretty accurately. But the output of that phase detector is a voltage that is directly proportional to the delta in phase, or the difference in phase, on an instantaneous basis between the test signal and some kind of a reference signal that comes from a reference generator. What actually comes out of this double balanced mixer is actually a sinusoidal voltage, and it's the product, it's a multiplication function of the two input sinusoids, right? We're injecting two sinusoids. One's the test sinusoid, signal under test, and my reference is the second one. And so we get, again, a little bit of math here, I apologize, but we get a cosine function, which is the difference and the sum of those two input signals. And if we put a low-pass filter at the output of that circuit, we end up being able to eliminate the second term in this equation, because it's twice the frequency. And we end up just with the voltage out being proportional to 1/2 of the voltages in times the cosine of the difference in phase at any instant in time. And that is our phase detector. That's what a phase detector basically does. And the nice thing about this approach now is that we are only limited by the phase noise of the reference source, but we don't suffer a lot of other losses or other noise in the measurement architecture. Now, one other aspect of the double balanced mixer design that's very important is that I said the output is a sinusoid itself, right? It's that cosine function. What we want to do is try to linearize that. And so what we do is we use another approximation technique. And you recognize that at the zero crossing of that cosine function in the region right around that sinusoidal trajectory is actually fairly linear. So what we're going to do is keep that reference source, that second signal generator, at a 90-degree offset at the exact same frequency, but at a 90-degree offset relative to my signal under test. And that's what's called the quadrature point, or keeping that source in quadrature with my test signal. And so to do that, we use a PLL, phase lock loop design, to make sure that our reference source is tuned at the exact same frequency and at a 90-degree phase offset on a time continuous basis relative to my device under test. And that's what's shown in that architecture here. And so now it's very easy to have a linear output voltage as a function of phase changes, as long as I'm close to this linear portion of the sinusoidal output. Okay? So by staying in the linear region, we can easily make phase noise measurements using that approach. Now there's one more issue that we can also address, and that is that I mentioned that the reference source here will still have some noise associated with it, and becomes a limiting factor in our ability to resolve and measure very, very low levels of phase noise. So we can use the benefit of common moding by cloning that whole measurement chain a second time and having a mirror image using a different reference source. And so now the noise associated with this source is uncorrelated with the noise associated with my first reference source, and I just split the output of my device under test into the two channels. So I have two identical channels with independent reference sources, and then if I do cross-correlation processing in my computer, I can actually reduce the effect over time very nicely in these two channels, and as a result actually get a pretty good improvement in sensitivity as long as I take the time to do those cross correlations. And it's based a very simple formula. For every factor of 10 increase in the number of correlations, I get about a minus 5 dB improvement, or a 5 dB improvement in sensitivity. And so for this reason, cross correlation is a nice feature to have in a phase noise measurement system. It does require twice the hardware. You have to have a second channel and a second signal generator as a reference, but it gives you quite a bit of improvement in the effective sensitivity or ability to measure very low levels of phase noise. So far we've been talking about absolute phase noise measurements. So measuring the absolute phase noise of a carrier signal of interest. There's a second class of measurements that are known as residual phase noise measurements. And in this case, we actually are measuring the phase noise that is added to a signal by a device. It could be an active device like an amplifier, or it could be a passive device like a switch or an RF cable. So residual measurements are done in a slightly different way. We still use our phase detector that I described earlier, but in this case, the device under test is here. Okay, we have a reference generator, and we split that between going into port 1 of the device under test, and the second part goes into a phase shifter. We use the phase shifter. It could be a delay line, or it could be an electronic phase shifter. We basically, again, want to maintain quadrature at the phase detector, just like before, so we can make a additive phase noise or residual phase noise measurement just on that device under test. So that's typical. It's a two-port measurement, an amplifier, cable, whatever that DUT is. We put that in the measurement path, and then we adjust the phase shifter on the other channel to get our output, which we then digitize and show on the analyzer screen. Okay, so residual phase noise measurements are also very, very important. So what are some of the solutions that are available today from KEYSIGHT? So the most common one is a spectrum analyzer. We have some measurement software. We call that a measurement application. It's an option to the spectrum analyzer, and that allows you to generate these types of phase noise measurement graphs, just like I showed you before. So that's a very common approach, but it has the disadvantage of being less sensitive than doing the carrier removal method that I described to you earlier. So for those kinds of applications that require higher sensitivity, we have two solutions today. We have a dedicated analyzer called a signal source analyzer. It's generally used for component developers that build oscillators or references that go into radar systems or digital communication systems. It has the two-port capability to do cross-correlation. That's why you see the multiple connectors on the front end. And the reference sources are internal to the instrument. So it's a self-contained unit, very easy to use, and is very, very commonly used in the component industry supporting the aerospace and defense industry. We also have a more complex high-performance system, which comes in the form of modules or different components. The E5500 actually uses external reference generators. Typically, it's a PSG with the best phase noise option, and it has a single channel only, so it doesn't do the cross-correlation, but it can do very complex measurements of pulsed RF devices. It can measure both absolute and residual, cover both of those measurement applications. So if you have a passive device or an amplifier you want to measure, we can do that with this system, the E5500. And most radar labs will have at least one of these if the designers are trying to characterize very, very low level phase noise, especially under pulsed conditions. All right, so in conclusion, I hope this wasn't too boring with all the math, but phase noise, while complex, is very important for our industry. We do have experts within KEYSIGHT and our local AEs here in the region that can help you make measurements, determine what the best approach is for your lab or your application. And we are working on new solutions for this all the time. So if you come back next year, we will have some exciting new technologies and products to talk to you about. All right, so that concludes my paper. Thank you very much. All right, Vishal, do we have time for questions or go through it? Yes.
Yeah, so we can have a couple of questions. And any more questions, we're going to have an extended break for prayer. Be for around 20 minutes. So we can have a couple of questions and then we can...
Okay. Yes.
We are talking about the phase noise, yes, that due to the phase drift from the local oscillator or from another radio frequency or microwave devices. In moving target indication radars, MTI radar, we use here two local oscillators. One is called coherent local oscillator, the other is called stable local oscillator.
Yes.
Both are the exciter portion of the local oscillator. So the output from both of those signals are transmitted, and the received signal will be extracted from the phase, from the Doppler frequency shift.
Yes.
The output, the final output will be supplied to the phase detector in order
Correct.
to,
Yeah.
yes, just this phenomenon is used in order to minimize the effect of the phase noise. Two local oscillators are employed in this technique. Yes, thank you.
Yeah.
Just remark, yes.
Yeah, thank you. Yeah. All right, maybe one more question. Yes.
Noise measurements. There is, we suppose that it is very linear. But what about when the time when is not very linear at the top of the sine wave at the time? Well, it can be also accumulated error in the measuring of the phase noise signals.
So I skipped a couple of slides in the paper. There's another technique called FM discrimination, where we actually use delay lines to be able to deal with larger phase deviations. Rather than using a phase detector, I can maybe I can show you during the break. I skipped a couple of slides, but there is another technique called FM discrimination that is useful for measuring noise devices that generate very large variations in phase, right? But for obvious reasons, we typically don't want those kinds of devices in our system. So in most cases, we are talking about narrowband phase modulation analysis. So that's where the techniques I showed today are more applicable. Yeah. Yeah. Yeah.
I forgot to thank you for this active presentation and a very interesting presentation.
Thank you. Yeah. Yeah. All right. Okay. Well, so I think now it's time for a prayer break. Yeah. Yeah. Thank you.